Okay, welcome back, everybody. Hope everybody had a good weekend. Okay, couple of just a quick announcements. Oh, let me let somebody in here. Okay, don't forget exam number 1 is due today. It should be open now. If it is open, I believe it shuts down at 11. Make sure you give yourself plenty of time. It's time allotted for 75 minutes. Average time in the past is about an hour. So make sure you give yourself plenty of time to complete it. It's a variety of questions, multiple choice, fill in the answer, short answer, so on, just like a regular in-person exam. Okay. So don't forget to knock that out today. Now, is there any questions concerning chapters 1 through 3? Okay. If not, I will continue where we left off. And that was in slide 9 of chapter 4. Okay, let me share that screen. We were talking about the atom and the model that we had for the atom. We just went through a scenario. Let's make sure that my sound is shared. Okay, we had just talked about the J.J. Thompson's work that demonstrated this particle he generated, denoted here by the red dots, that were shot across his ray gun, if you will, and it hit the surface of this material that was covered with a fluorescent compound. Well, the energy on the red dots was transferred to the molecules on the screen, and they absorbed it, but nature being nature, it's not gonna, nature doesn't like to stay up in that excited state. It eventually drop back down, and when it does, it emitted the energy it gained with a light. So he was able to observe something happening over here in the far right, on the other side of the screen. He then went on to put a electrical field with a plus and a negative side, and demonstrated that he could deflect this ray that was being generated, okay, by simply changing the polarity of the electric field. And then I also stated that for any charged particle that is moving, coupled with it, tandem to it, is a what we call a magnetic property. So any electrical, like any electrical current that is moving, perpendicular to it is a magnetic component, which is a good property because it allows us to generate motors and generators. That's how we create electricity with generators, by playing with the magnetic component of an electric charge. So he demonstrated, JJ did, that by putting a magnet, he was able also to deflect this charged particle. He also went on to determine the ratio of the charge to mass ratio, which he was then eventually was able to calculate the actual mass of this electron. So his work is very important because when J.J. Thompson is accredited with discovering the electron. So he presented a model of the atom, which became known as the plum pudding model. Okay, so basically, there's electrons are in the atom someplace. Nothing very specific. We're going to learn that we're actually going to be talking about these electrons existing in very specific wavelengths. Okay, but that's here in a little bit. And there's a positive component of the atom somewhere. Okay, so that was called the plum pudding model. Well, that's 1904. Here comes another English scientist by the name of Ernest Rutherford, 1911. Now, what he is credited we're discovering is basically the nucleus slash the proton, okay? And what he did, he used a particle generator, again, called alpha particles. And they're going to talk about those, but what he did was generate these particles, and he shot them at a gold foil, okay? Now, much like JJ's system, where he had a fluorescent screen, Rutherford also had a screen that kind of circular surrounded the whole instrument that he was utilizing. Now, what he anticipated, based on the plum pudding model, that all these particles would just go right through the gold molecules in the gold and generate a image on the other side of the screen, okay? To his surprise, they weren't doing it. Yes, the majority of them were doing that, but there was some occasionally a particle that was being ricocheted. It's actually ricocheted all the way back to the detector itself, or the source of the particles. And so they were angling off. So what that suggested, that there must be a very dense component of the atom, because these particles were being ricocheted, just like shooting pool. You hit the ball, the cue ball hits another ball, and going to hit the corner pocket. Okay, so let's listen to that video.
In 1910, Rutherford and his co-workers were...
Okay, can everyone hear the sound? Or who cannot hear the sound? Do that way. All right. Oh, we got one. Yep. Okay. Anna. Sounds good. All right, let's continue.
Studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were...
Notice here that the majority of the alpha particles were traveling, and they're hitting, and they go right through the foil and generating the fluorescent light on this side here, okay? But occasionally, you can see the ricochet, the light, it lights up here on this side and then that side, all over the place.
Found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So based on Rutherford's work, a new model came forward a few years later. That's what the way science goes, More data comes out and we get to reinvent the wheel, if you will. So we have Thompson's model on the left, which was called the plum pudding. And then based on Rutherford's work, he proposed that there's got to be a nucleus, very dense material. And sure enough, that's where our model is, where in the nucleus consists the proton with a positive charge. And then the electrons, we're going to learn, are orbiting around the nucleus in specific energy levels, okay? Specific energy levels. And so 1917, Rutherford is credited with the discovery of the proton. We have JJ, 1907, roughly, the turn of the century there, 1900s. He's credited with the electron, but the neutron really didn't come out discovered until the 1930s, again, by another English scientist, James Chadwick, okay? So now we have a general model where we have the nucleus and the proton, proton and the neutron are in the nucleus, and then the electron is orbiting in specific orbits around the nucleus. Kind of in general terms, means or ways is like that image here on the far right, okay? But we're going to have more specific information here in a bit. Now, the atom itself is just basically a lot of empty space. if I were to scale down the atom or scale up the atom of the hydrogen atom, okay? First element, the first element, number one, has one proton and one electron. If I represented the nucleus of the proton of the hydrogen atom, my electron, relatively speaking, will be roughly about 3/4 of a mile away. That's quite a distance, and yet that attraction, that force is quite strong, quite strong. Okay. Another perspective, if the nucleus is the size of, say, a small marble, then the atom would be roughly the size of, the whole Cardinal Stadium. So a lot of empty space in between. Okay, so the subatomic particles that we're going to be dealing with are given as follows. Okay, yes, these subatomic particles are made up of even smaller particles, but that's beyond the scope of Chem 130. We're going to talk about the electron, the proton, and the neutron. Okay, the electron is noted by its symbol is noted by the letter E, and it's got a superscript. Oh, something going on with my pen here. Uh-oh. All right, well, okay, well, I got the electrons in here, and it's denoted by the letter E with a superscript negative charge, okay? The proton, its position is outside the nucleus, and we give it a charge of a -1, okay? Now, the proton is denoted by the letter or lowercase p with superscript plus symbol. It is inside in the center of the nucleus, and it has a charge of a +1. A neutron, obviously, guess what? No charge, as a neutral species. It's also located inside the nucleus with the proton, okay? Notice the charges of the electron and the proton. So overall, the elements themselves, they start off with, for example, hydrogen has one proton and one electron. Therefore, its overall charge is, net charge is 0, because the plus and the negative cancel each other out. We're going to learn that these atoms will, depending which ones they are, will either gain electrons or lose electrons. The driving force is to maintain that magical 8 number that these atoms are striving for. But in the process of gaining or losing electrons, they no longer become the elements. They become what are called ions, okay? And they're going to have their net charge changes. And so if an element loses an electron, it loses negativity, then the new net, if I were to lose this negative here, then my net would be a positive charge. And that's what happens with hydrogen. If it loses that one electron, which it will, then its net charge is a positive charge. On the other hand, in an example, what if it were to gain an electron? So now it has 2 negative charges and 1 plus charge. So now the new net is a -1, okay? So you see how that works? So it's a general rule, which is probably like 99% of the time, 99.99% of the time, all metals want to lose electrons, okay? So you might want to put that in your long-term memory here. In contrast to non-metals that want to gain electrons. And in the process, as I stated, we'll see more in here in a bit when we start learning in the next chapter, and we start learning about the electrons, in that when they lose or gain electrons, their new charge, their new environment will put them in a manner such that it has a net positive, a net 8 electrons around the shell, okay? All right, so now with respect to the mass, oh, there you go. It must be my pen that's acting up. Yes, it is. Bear with me for 1 second. I'm gonna do some technical thing here. Okay. All right. All right. With respect, one last thing before I forget. The last column what we talk about here is a relative mass, or AMU, which is the atomic mass unit. What has been done is we give them a relative mass. These masses of the proton and neutrons are very, very tiny. And so instead of giving them some number of 10 to the negative whatever grams or kilograms, we give them a relative number. So what's been assigned to the proton and the neutron is a relative mass of 1. Okay. It's much like, me, I'm sitting here maybe at 200 pounds, right? Someone else is over there weighs 400 pounds. So they're twice my weight. So their relative mass, I would be a 1. Their relative mass would be a 2. Okay. And that's how that's done here with respect to the protons. So the electrons are so tiny. To give you an idea, they're 1 and relative mass is 1 over about almost 2,000. Okay. So essentially 0. And that's what's been done is the mass of electrons have been assigned a relative AMU of 0. Keep in mind that yes, it has a relative mass of 0. There's still mass, but it's so tiny. We're going to learn that these electrons behave like light because of their mass being so small. Okay. All right. Now, with respect to what we call atomic notation and how we present what the the atom is with its symbol, and we define what's called A here, the upper left superscript on the A side. That is the mass number, which is always a whole number. And then on the bottom left, okay, subscript left, Z denotes the atomic number, which is also a whole number, okay? The symbol then is in the center, like SY for the symbol, and that will be the notation. Now, keep in mind also that the mass number here written in this format is always much, much bigger than the atomic number. There's 118 elements, the atomic number from 1 to 118. Okay, 1 represents hydrogen. Now, it also represents, the atomic number represents the number of protons, okay, plus the number of electrons. So element number 1, hydrogen, has 1 proton and 1 electron. Okay. The mass number, okay, being a whole number, is represented by the number of protons it has, which is the atomic number, plus the number of neutrons, okay? Number of neutrons. Bear with me for 1 second, please. And let's see. Let me stop for a second. I need to give me about 5 minutes. I gotta figure out how to fix my pen because I really need it. All right, I think I fixed it. All right, let's try this again. Okay, so the symbol denoted by the letter SY, very generic, general information there. And then the mass number, okay, both of these, mass number and atomic number, always whole numbers, okay? Not to be confused with the number under, if you look at the periodic table, underneath the symbol, there is a decimal number. That is called the atomic weight, okay? The atomic weight. For example, if you look at carbon underneath the symbol, you got 12.01 with the number 6 on top. If you look at your periodic table, the mass number, the atomic number is 6 for carbon. Its atomic weight is 12.011. Now we're going to learn that this number here, which is a decimal number, is the average of whole numbers, okay? In fact, specifically, it is the weighted average of whole numbers. So, for example, let me for example, and we'll put it all together here in a second. All right, let's take the numbers 4 and 5. Okay, what is the average of those numbers? What is the average of 4 and 5? You can tell me that. Yeah, 4.5. Exactly. The average is 4.5. Now notice these are whole numbers. These are decimal numbers. Okay. So the atomic weights are the average of whole numbers. Therefore, they have an infinite number of significant digits, infinite number. And that's point number one, is the atomic weights, we don't utilize them to determine significant figures because they have an infinite number of significant figures, so we don't utilize them. But if, for example, the 4, and we were counting the number of times we were throwing the numbers 4 and 5 out there. Okay, we did this 1,000 times. So 90% of the time, maybe the 4 popped up, meaning that 10% of the time, the 5 number popped up. Now we have what's called a weighted average. And instead of being, this is not weighted here, just the average of those two numbers. Now, we have to include the 90% and the 10%. So now our average might be closer to 4.1, okay? And that would be the average of the numbers 4 and 5, the weighted average. And the reason it's closer to 4.1 is because more times there's more 4s than there are 5s, okay? So let's go back to the elements. We have carbon, 4 types of carbon. And we denote it by carbon and then hyphen 11, carbon, hyphen 12, carbon, hyphen 13, and carbon, hyphen 14, okay? Now, all of them are carbon. All of them are carbon, okay? And so the atomic number for carbon is always 6. In fact, and that being the case, that tells us that we have 6. Let me erase some of this here. We have 6 protons and 6 electrons, okay? All right. These here, carbon 11, carbon 12, carbon 13, carbon 14, are what we call isotopes. They are all carbon, but they're different in the way and the number of neutrons that they have, okay? So if we take the mass number This will become hopefully clearer in a second. If we take the mass number and because remember the number of protons, the mass number is the number of protons plus the number of neutrons, okay? And so if we take that, rearrange that and say mass number minus the number of protons will equal the number of neutrons, okay? So the mass number here is 11. Okay? So 11 minus 6 equals 5. That is the number of neutrons for carbon 11. 12 minus 6 equals 6. Carbon 12 has 6 neutrons. Carbon 13 has 7 neutrons. And carbon 14, and I'm sure you've heard these carbon 12, carbon 13, carbon 14 dating. Okay, these are isotopes of carbon, okay? And note here, all of them have 6 protons. That is what defines these elements here on my screen. That element, if it has 6 protons, is carbon. The moment I lose or gain a proton, I have a totally new element. I will lose neutrons and electrons all day, lose or gain them all day long. And it has no effect as to what element I'm working on. So the protons is what defines. Now, these isotopes, okay, carbon, there's a percentage of carbon in nature, okay? And so if we were to average these numbers up, 11, 12, 13, and 14, what would be the average, you think, of the numbers 11, 12, 13, and 14? Straightforward average, what would that be? About 12 and a half, exactly. It's like we did the earlier one. But in nature, they have a different percentage in nature. I want to say off the top of my head is about 98% of the carbon in the world. I mean, out there. Oh, sorry. I say it. That's my dog back here. Theo, go play your toy over here. He's over here squeaking his toy. Go. Yeah, sorry about that. All right, so out in nature, carbon exists about, there's about 98% of the isotope carbon. The 11, the 13, and okay, I need to find something else. Let me put him on the garage. Be right back. All right, let's go. Come on, let's go. All right, my apologies. The fun aspect of online teaching. All right, so as I was saying, carbon, yeah, exactly. I wish I had his energy. And so as I was stating, these carbon 11, 12, 13, 14, this is just for carbon. It also exists with the other elements. There are different numbers of isotopes, but this is going to explain why we don't utilize that number. So like we just did the weighted average example of the numbers 4 and 5, we do the same thing here. And with the weighted average of carbon, okay, it's roughly 1%, trace amount, roughly about 1% here, ballpark. Okay, so with that being the case, our weighted average now is 12.01. Okay, with that information, that's what you find on the product table below the symbol, the atomic weight. And because that is the weighted average of whole numbers, we don't utilize it to determine whether they play a role in sig figs. We're going to use those numbers down the road to do some calculations. Now, what I can also do with this information is state the following. By looking at the atomic weights on the periodic table that you have and taking the atomic weight and rounding up to the nearest whole number, that can determine the most common, most abundant isotope for that element. So if I take the example of 12.01 and I round it up to the nearest whole number, guess what? I get 12, which tells me carbon 12 is the most abundant isotope that there is. And I can do that for any of the elements on the periodic table, okay? Also, it would help me, once I do that, to determine number of neutrons, because I can round up the atomic weight of the most common isotope, would give me 12, subtract the atomic number, okay? And I get 6 neutrons. So the most common isotope of carbon has 6 neutrons, 6 protons, 6 electrons, okay? The least common ones have carbon 12 have 5 neutrons for this one here, for carbon 11. It still has 6 electrons. Don't forget that, always that's consistent. What changes is the number of neutrons, which actually puts more weight on it, okay? More weight, so it's like carrying extra baggage. All right, so let's go back to here. And so like I stated, the mass number is equal to the number of protons plus the number of neutrons, okay? Now, the number of protons defines what that element is, okay? That's the definition of that element. So, and also the number of protons equal the number of electrons. Right now, we're just talking about the elements right now. So they're going to end up with a neutral charge. All the elements behind my head here have a net neutral charge of 0 because they have the equal number of protons, which are positive, and an equal number of electrons, which are negative, okay? And the number of protons defines an element. You can lose neutrons, you can lose electrons, and you don't change what that element is. But the moment you lose a proton, which is quite frankly quite a little difficult unless you're a radioactive material. And when that happens, you know, the products you create are, you know, some deadly rays and some other radioactive material. Okay, so it's not an easy thing to lose protons. Okay, so we talked about carbon. Okay, carbon always has 6 protons and 6 electrons, regardless in the form that it's in. The carbon, let's say in a fiber of, say, a fatty acid, has 6 protons, compared to carbon in carbon dioxide. Still has 6 protons. It is still carbon, it's just in a different format. Okay. So I talked about the atomic mass units because of being so small. The proton and neutrons are given a relative atomic mass unit of 1, and the electron basically given a 0 because it's so small. So mass number, by definition, is the sum of the number of protons and the number of neutrons. So how do we calculate the neutrons? Well, no problem. We rearrange that equation where the number of neutrons equals the mass number minus the number of protons, okay? The mass number we obtain is from the periodic table. So we will, 1 second. And so if we go to the periodic table and this red and so forth, we're going to learn more about that in the future here, but ignore it for right now, these circled elements. But going to the periodic table and picking any element that you want. For example, we talked about carbon. Notice carbon has an atomic weight, which is a weighted average of 12.01, okay? And so taking that number and rounding it up to the nearest whole number, we get 12. So carbon 12, okay, written by carbon-12 is the most common isotope, okay? If we look at nitrogen, what would be the most common isotope of nitrogen? What would be the most common isotope of nitrogen? What do you guys think? Simply take
would be the halogen or the Ne, whatever that is.
No. I'm right here in nitrogen. When I state isotope, I'm talking within the element. Okay, so right now I'm talking about the most common isotope of nitrogen, and nothing to do with any of the other elements. Okay, what do I need to do? I take the atomic weight, which I've highlighted, round it up to the nearest whole number. So what would be the most common isotope? What number would that be?
14.01.
Well, round that up. Round this number up to the nearest whole number. What would it be? 14. There you go. Okay. So I would write the most common isotope for nitrogen would be nitrogen-14. Okay. If I were asked the question, what is the most common isotope for sulfur? What would I say? Well, I would write out sulfur.
32.
32, exactly. Okay. That is the most common isotope for those particular elements. Let's look at copper. What would be the most common isotope for copper?
64.
You got it. Okay, that would be copper -64. Okay, you round it up to the nearest whole number. And you can do that for any of the elements. The only one that you can't do that for is basically these in parentheses. The ones in parentheses, these are man-made, and they're so unstable, I should say, that they really haven't gotten enough of it to last long enough to do any study of it. So any decimal number, you can do that. Anyone with a decimal number. And that generally brings you up to about 90, roughly 85 there. Let me see. Yeah, anything with the isotope with parentheses would be difficult. Okay, so again, that is the weighted average. That means that, clear this. Yes, you were going to learn that some of these have 2, 3, 4, 5 different isotopes of itself, of that element, okay? But because of the amount of quantity in nature, we have to do a weighted average of all those isotopes, and we end up with the decimal number, okay? And by rounding up to the nearest whole number, that tells us that we can determine who is the most common isotope for that particular element. Okay. Now, what can happen at times is they tell you what isotope you're working with. Here's an example. Okay, look at this one. Potassium 40. Now, can you tell me if potassium 40 is the most common isotope? Okay. What do you think? Well, let's go find potassium. Potassium's number 19. What is the most common isotope of potassium?
$39.
You got it, okay? But the question is asking about potassium 40, okay? So that means that potassium 40 is not the most common isotope, okay? But you can calculate even that, you don't have to average a number out. Why? Because it's given to you right there. That is the number. So the most common isotope would be potassium 39. So what do you think the difference is between 39 and 40? They're both potassium. They both have 19. They have 19 protons. They have 19 electrons. Where they differ is the number of neutrons, okay? So how do I calculate that, okay? Here's the question. So let's do this. Now, first of all, let's write the notation, which is we got to find the symbol for potassium, which is K, okay? The mass number is given to you. You don't have to look that up. It's the number after the hyphen, that's 40. And the atomic number, you have to go look for it in the periodic table. It is number 19, okay? So if I needed to write the atomic notation for potassium 39, guess how I would do it? It would be 39, K, and 19, okay? So both of them share the number of protons. Both of them share the number of electrons. I wrote that wrong there. Let me correct that. Okay. Where they differ would be the number of neutrons. Okay. So for potassium 40, it's simply 40 minus 19. There are 21 neutrons for potassium 40. How many neutrons would there be for potassium 39? What do you think?
20.
20, exactly. So 39 minus 19 is equal to 20 neutrons, okay? So the most common isotope for potassium is potassium 39, okay? Both of these have 19 protons, and both of them have 19 electrons. Where they differ is the number of neutrons. Potassium 40 has 21 neutrons, and potassium 39 has 20 neutrons, okay? So if the question is asking you to determine the number of neutrons for a particular isotope, it is going to tell you the mass number written in this form, okay? Sometimes you may see it with the symbol like K-40. That is potassium 40, okay? Like earlier we did carbon. Sometimes instead of writing out the name carbon, you may see it as C-12, carbon 12, or C-14, carbon 14. If that information is not given, then you can go to the periodic table and assume we're talking about the questions asking about the most common isotope, and just take that atomic weight, round it up to the nearest whole number, and work from there to determine the number of neutrons. Okay. For example, you might think, oh, not quite sure. Well, let's do a quick one. All right, let's take iron right here. Question would be, how many neutrons does iron have? Okay, so how can I figure that out? What do you suggest? Okay, they didn't give you the specific isotope. They just asked the question, how many neutrons does iron have? So what can you assume from that question? That iron, whatever's on the periodic table, we're going to use the most common isotope. So what is the most common isotope of iron?
56.
You got it. And so now I can write it, and I'm going to put it over here. I can say iron 56, and the number is 26. Now, who can tell me how many neutrons iron 56 has?
$30.
You got it. Good job, 30. So iron, most common isotope, iron 56 has 30 neutrons, okay?
Hold up. Where did you get the 30? Oh, did you? Oh, never mind. Never mind.
Okay, 56 minus 26, okay? And the question was asked, what is the most common isotope for element? Let's do chrome, okay? How many neutrons does, well, first of all, let me ask the question for chrome. Let me clear this up a little bit, okay? And we're working with chrome, okay? First question, how many neutrons, not neutron, how many protons does chrome have?
$52.
No,
24.
you got it. Okay, we're looking at chrome, and so protons is 24 for chrome. Okay, what about electrons?
52.
No,
Or 24.
24, you got it. Okay, remember and what is the most common isotope of chrome?
That's 52.
There you go. So we can write that chrome 24. Okay, now we can ask the question, how many neutrons does chrome have?
28.
28 neutrons, 52 minus 24, okay? So either it could be chrome, sometimes it could be chrome 53, or even chrome 51, or sometimes even more than that. But if you're not working with the most common isotope, okay, then you can assume the question deals with the most common isotope. Otherwise, the question would be like that. It'll say, write the notation for potassium 40. They are telling you which isotope you're working with, okay? And as we just showed you earlier, that potassium 40 is not the most common isotope. Potassium 39, okay? All right. All right, so here, the question is, write the atomic notation for bromine 81. So the first question I would ask is bromine 81 the most common isotope?
It would be 80.
It would be 80 exactly. So they're telling you the specific isotope you're working with. So the most common isotope, because it would be bromine 80, and you determine that by looking at the atomic weight of 79.99. Is that 99? No, 90. That's for bromine. Okay. And so what about the atomic number for bromine? What is that?
35.
35. So the notation for both of them is as follows. Okay. You got 81 in upper left, superscript left, and you're told what that mass number is. So you don't have to search for it. Okay. It's right there. Okay. And then both of these have the same, it's still bromine. Okay. Nothing's changed. It still has the same number of protons. So how many electrons does bromine have?
35.
35 electrons and 35 protons. And where they differ now is neutrons. How many neutrons does bromine 81 have?
46.
46. And how about bromine 80?
It would be 47. No.
No, the other way.
45.
45, one less. Okay. So, in a nutshell, you learn, finding the element. You can determine the number of protons, the number of electrons, and if you're dealing with the most common isotope, you can determine the number of neutrons for that particular element. Okay. If it's not told to you which isotope you're working with, you can do that. But otherwise, most of the time, they'll tell you what isotope you're working with, and then you can work the numbers from there. Okay. All right. And just remember that the mass number is always a whole number, just like the atomic number, always a whole number. The only decimal number here is the atomic weight, okay? That is the only number. And so the atomic weight doesn't belong anywhere in the atomic notation of the elements. And so here we have 46 neutrons for bromine 81 and 45 for bromine 80. All right, this is basically what I talked about carbon, an example, all the different isotopes. All of these carbon, they're not mentioned 11, but we got carbon 11, 12, 13, and 14. See, all of them have 6 protons. All of them are carbon. We haven't changed what that element is. Where they differ is the number of neutrons, okay? And so carbon 14 is a little bit heavier, and being heavier, it's a lot more unstable, and will break down to go back to carbon 12 or a more stable state. And we can utilize that breakdown is because it breaks down at a very specific rate. We can use that to give some approximation and calculations of how old things are by measuring their decay or the quantity of the isotope. All right, now we got oxygen here. Notice there, which oxygen isotope is the most common isotope? Now here we're given oxygen 16, 17, and 18. Of these 3, which one is the most common isotope?
$16.
16, exactly. All you have to do is go to the periodic table. Remember that little table? Look up oxygen, number 8. Its atomic mass here, atomic weight is 16.00. It's already there for you. It's a whole number, oxygen 16. Now, the mass number is given to you there. So you don't have to calculate anything because the mass number is given. 16, 17, and 18, okay? What about the number of protons? How many protons does oxygen have? Oxygen 16.
8.
8, exactly. What about 17?
8.
8, and the same is true for 18. And that is also true for the electrons. Right now we're talking with the elements, we're talking about the elements. And so they're going to have equal number of protons, equal number of electrons with a net charge of 0. We're going to start learning about these ions because once you start gaining electrons or losing electrons, you end up with a net positive or negative charge. Now, that being the case, the only differ is in the number of neutrons. So we got how many neutrons for oxygen 16?
8.
8. And what about oxygen 17?
9.
9. And then we got, and finally 10, right? So you notice here, that's the only difference. All of them are oxygen, okay? Denoted by the number of protons, but they differ in amount of weight that they carry. Okay. Now, that means that oxygen 16 is, like I said, the most common isotope, and it's probably about a 99% amount in nature, and obviously less than 1%. So we incorporate these percentages into these whole numbers. You can see the average, weighted average is closer to 16, and therefore that is why we can average out or take the atomic weight and move it and round it up to the nearest whole number to give us the most common isotope. All right, so boom, there you go, 8, 9, and 10. All right, this is again carbon 13, give you a little bit more information about weighted average. There's trace amounts of carbon 11. I was a little bit high. Yeah, 98.89% for carbon 12 in nature, or about 1% of carbon 13, and small amounts or minor amounts for carbon 14. Again, that allows us to do a weighted average. And when we account for this percentage, when we accommodate for these percentages, we end up with an average of these numbers of 12.01. Okay, that is our atomic weight. And like I stated, these atomic weights that we have on the periodic table are the average of whole numbers. Those are whole numbers, the weighted average specifically, and therefore have an infinite number of sig figs. So don't use the atomic weights in determining the number of sig figs that you're going to do in your calculations. Okay. Now, an added note about all these atomic weights. All these atomic weights have units. You know, even though I'm throwing the number out, 12.01, guess what? They have a unit. And specifically, they have the units of grams per mole. Okay, guess what? It's another ratio that we can utilize with moles in the numerator or moles in the denominator. So we do calculations because we're going to be able to take that atomic weight in grams of copper, and from grams of copper, determine how many moles there is, and from that information, determine actually how many atoms of carbon we're working with. Okay, which are going to be a big giant number, so we're going to have to convert it to scientific notation. Which reminds me about scientific notation. If you're having a challenge in your calculator with respect to inputting your number in into scientific notation format, please let me know, because I had yesterday I gave my exam to my other GCC class, And I had one student who was trying to, he thought was using the correct format or the correct way to put in scientific notation to calculator. He was taking the number, but then he was hitting the time symbol and then the 10 to the X power. But that's not scientific notation. So remember, if you're using scientific notation, you have a button specifically for the scientific notation format in your calculator, okay? All right, so let's continue. And with that being said, you can have questions like, all right, lithium-6 versus lithium-7, right? Which one do you think is the most common or most abundant isotope? I think abundant would be a better term to use, I guess, which is the most abundant. Lithium, which is Li, lithium-6 or lithium-7? What do you guys think? Well, that's where you use the periodic table. Okay?
Lithium-7.
You got it. Lithium-7, because you go through the periodic table. Lithium-7 has an atomic weight of 6.94, rounded up to the nearest whole number, and you end up with lithium-7 being the most abundant isotope. Okay. Both of them share the number of protons of 3. Both of them share the number of electrons. Remember, what they differ is in the number of neutrons. All right, here's one. We got chlorine-35 and chlorine-37. What do you guys think? Which is the most abundant isotope?
35.
35, exactly. Because 30, you go to the periodic table, chlorine has, which is element number 17, okay? And its atomic weight is 35.45, rounding it up to the nearest whole number gives you chlorine-35, okay? I can't overemphasize both of these, chlorine-35, chlorine-37, both of them have 17 protons, 17 electrons. Where they differ is the number of neutrons, okay? So you can take that 35, subtract 17, that gives you a number of neutrons. Take 37, subtract 17, that gives you a number of neutrons for chlorine-37. All right, a lot of these, well, I shouldn't a lot, but there are some that are radioactive, and I mentioned that they break down. You can see like element number 96, which is named curium. Okay, any idea? Well, actually, it was named after Madame Curie. And just a little side note here. Anybody know by chance where Madame Curie's from? You ever heard of her? We owe her a lot, at least in the health industry. She did a lot of work about using X-rays. In fact, she got 2 Nobel Prizes, by the way, and her kids also got a Nobel Prize. So a smart family. Okay, but does anybody know for where Madame Curie might be from originally? The name itself would suggest France, but her husband was French, and she ended up in France. She's originally from Poland, and during her time period, she left Poland because she wanted to get a higher education. At that time, women were not allowed to get a higher education in Poland. And France was the mecca of a lot of science, France and Germany and England. And so she went to went to France to get her doctorate and got her doctorate. Very famous doctorate, by the way. Very unique work. Anyway, she did a lot of work with radioactive material, got involved with using X-rays and to take X-ray pictures of broken bones and etc. And went around the country, making sure everybody learned about it, and actually died from the effects of radioactive poisoning. Because at that time they were not quite sure about the effects and these particles that were happening. the mind-boggling, the reason I know a lot about her, I had to write a paper for her, for a scientific paper. She extracted literally a mountain full of material to get a few milligrams of a radioactive material. So anyway, she was a chemist by background. Anyway, Madame Curie. Let's kind of shift gears a little bit, and we're going to briefly talk about chemical formulas. We're not going to learn about how to name them, what they are. We want to identify. Madame Curie, Curie. The name, an element is named after her. This one, number 96, curium. All right. Well, we're going to kind of shift gears a little bit and talk about chemical formulas. We're not going to learn about how to put them together or what their names are. I'm going to tell you what they are. But the point of this exercise is to identify how many elements we have in a particular formula. Okay, we're going to, down the road, we're going to have to do that to learn how many hydrogens a formula have, how many carbons, how many nitrogens, because we're going to take that number and multiply the number of carbons by its atomic weight for carbon, number of nitrogens by its atomic weight, and sum everything out to get an atomic weight for the whole molecule. And then that information we're going to utilize to do some more calculations. Okay. All right. So like I say, it's not going to tell us about in order here. We're just going to learn how to count the number of atoms involved. Subscripts are utilized. That just tells you how many elements of that particular element are in the formula. But if there isn't a subscript, it's understood to be a 1 or left blank. Okay, just like in mathematics. Like for example, H2O means there are 2 hydrogen atoms and 1 oxygen atom, which is a total of 3 atoms total. Okay, had nothing to do with bonding. Hydrogen is not bonded to hydrogen. We're going to learn how hydrogen is bonded down the road. Okay. We have this formula here. Okay, we have C3H sub 6 and oxygen sub 3. Okay, which tells us there are 3 carbons, 6 hydrogens, and 3 oxygen atoms. With that information, we're going to take that information and we're going to say, okay, there are 3 carbons at 12.01, and there are 6 hydrogens at 1.01, and there are 3 oxygens at 16.00. When we do that math, we tally all that up, and we're going to have what's called the molar mass of that compound right here. Okay. And this is the general way of writing the formula. I'll tell you what it is. It's acetic acid or vinegar. But that information is important because we're going to need this for calculations. Not only that, we can also determine the percentage that this molecule, that carbon attributes to the overall percentage of this carbon, of this molecule. So if we got what here, 36.03 grams, we got 6.06 over here, and we got 48.00 grams. Okay, and if we add this up, check my math, we got 0.09, 14, and 620, 789, 90.09 grams per mole. That is a total mass, total atomic weight, total molar mass for this particular chemical formula. And if we take that 36.01, remember we did a parts over whole. All right, we take that 36.03 and divide it by 90 times 100, that gives us the percentage of carbon. We can do the same for hydrogen and do the same for oxygen, okay? All right, so, but we have to identify how many atoms of each, identify how many atoms we're working with, so we can do that type of calculation. All right, now, we have this example here. You see a parentheses. Now I'll bring to a point here. Whenever you see a parentheses in the formula, what it means is it is a unit. It is a unit that we're going to learn quite a bit about. Okay, and I'm going to direct you to the periodic table. If you look at your periodic table, scroll down, and there, go to the bottom left corner. You'll see right here, these compounds, these formulas that are called polyatomic ions. These are packets. These are units that we're going to learn a lot more about. And we keep them together as a unit. And if we need to add more of them, we need to utilize more. We use a parentheses to identify that we have 2 of them, 3 of them, 4 of them, whatever number we need. Notice that these ions have a charge. They have a negative charge, okay? Sometimes we need 2 of those nitrates. This is this one up here. One added aspect about these is they have their own specific name. We don't change their name, okay? That species, NO3 with a negative charge, is called nitrate. Not called nitrogen oxide, nothing of the sort. It has its very specific name. Differ from the next one down. It only has 2 oxygens, but still has a negative charge, and that is called nitrite, okay? And if I need to use more than one, like I stated, I use a parentheses to identify that I'm using more than one, like in this case. See that NH4, okay, in that parentheses, guess what that is? Let's go back to periodic table. NH4, that is called the ammonium ion, okay? It has a plus charge. And that is the reason we're putting 2 of them here, because we're going to learn that CO3 overall, which is called the carbonate, has a, oh, you're getting a lot of good stuff ahead of time, has a -2 charge. The CO3, look at this, CO3, it's called a carbonate. You're using the ammonium, okay? If you had to take a wild guess, let's get your brain gears working. That species we have right now is on the chapter, they've got NH4 parentheses 2, then CO3, okay? Now, if I had to name it, if I had to name this species compound, what does your intuition tell you its name would be? What do you think? Because I'm using ammonium, I'm using carbonate. What do you think this name would be?
Ammonium carbonate.
You got it. See how, and if I wasn't using carbonate, I could be using nitrate, and that would be ammonium nitrate, or nitrite, or sulfate, or sulfite, or phosphate, or et cetera, et cetera. So, we're going to start building up your database of all the compounds. We do like a mix and match, okay? I have the ammonium acetate, ammonium hydroxide, ammonium cyanide, ammonium permanganate, and we put the plus and the negative together. And the reason we put a parentheses here, because notice the carbonate has a -2. The ammonium has a +1. I have to put enough of positives and negatives together so they cancel each other out. And since each ammonium has a +1, I need 2 of them. And since I need 2 of them, I have to put a parentheses around it. Okay. And it's called ammonium carbonate. And I have to put a 2 around it to designate 2 of them. I don't do N2H8. No, I don't. Okay. I don't know what N2H8 is. It's 1 unit of the ammonium ion, and I need 2 of them, so I put a parentheses. Okay. All right. And the name, like I said, ammonia. So you already start your database. So I already just my mix and match here. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 compounds. Okay. And then this I can replace any metal, any ammonium, and replace it with sodium and say sodium nitrate, sodium nitrite, sodium sulfate, sodium sulfite, etc., etc. You know, in a few weeks, you're going to have a database of chemical compounds, maybe a few thousand compounds. All right, let's go back. All right, so the point, a lot of additional information, and that's okay, because we're going to get it again. That way you won't be, surprised, like, whoa, here, it's an introduction into a more in-depth detail down the road here. So the point here is to identify how many atoms of each one you have. So if you look at in the parentheses, there's a subscript 2, meaning there's 2 ammonium ions, which tells you there are 2 nitrogens and a total of 8 hydrogens. There's 1 carbon and 3 oxygens. So that has a total of 14 atoms, okay, for this ammonium carbonate formula. And 14 atoms. Now, at this time, knowing how many the atomic weights of nitrogen, I multiply that by 2. Hydrogen is 1.01 for each one, multiply that by 8. 1 carbon at 12.01, 3 oxygens at 16. Tally all that up, and that gives you the molar mass for ammonium carbonate, okay, which we can use down the road with respect to calculations. And that's important here that we get the right molar mass. So we have to identify how many atoms of each we have, okay? All right, so how about this one? Here we have H3PO4. Again, well, where you may not be familiar with what this is, but I'm going to tell you anyway. If you drink a lot of soda pop, like I do, you drink a lot of this. This is phosphoric acid, by the way, H3PO4. We have 3 hydrogens, 1 phosphorus, and 4 oxygens, okay? Well, calcium, hey, let's do this. Look, we got a parentheses, okay? We got a parenthesis, so that tells you something. So let's, and Ca, is its name is calcium, but you may not know what this OH is, but the fact that you recognize you have a parentheses should direct you to the atomic periodic table and look for OH here. Look at this, OH right here. It's a -1, and it's called hydroxide. That's its name. So with that being said, what do you think the name would be for this compound? For this one right here. This is calcium. We just learned that this is OH, is called hydroxide. So its name would be calcium hydroxide. Okay. You probably find this a lot in, you might read the label, I'm pretty sure you find it in Tom's or Maalox, I forget which one. This is a base. So you have 1 calcium, there are 2 oxygens total, okay? And there are 2 hydrogens, so there's a total of 5 atoms, okay? The next one, good old Al, is aluminum. But here we go again with the parentheses, and we have SO4. If you had to name that, the fact that you got a parentheses should send you over to periodic table, and here we got SO4 right here. Its name is called sulfate. So what would be the name of that species? Right here. Al, which is aluminum, and SO4, which will be sulfate. Okay, aluminum sulfate. Okay, so aluminum sulfate has 2 aluminum, 3 sulfurs, 12 oxygens, or a total of 17 atoms. See how you got 12? Okay, 12, and there are 3 sulfates, to a total of 12 oxygens. All right. Okay, so the law of definite composition is, as we began the study on the atoms, the elements and so forth, and kind of introduce you to the formulas. We mentioned earlier that when the atoms come together, that they come together in whole numbers, okay, not quarter numbers or anything like that. So H2O comes with 2 hydrogens and 1 oxygen. So its composition is 11.2% hydrogen and 88.8% oxygen. You might ask, well, how did that come about? Well, we know the formula is H2O. We know there are 2 hydrogens at 1.01 for each hydrogen. That's the atomic weight on the periodic table. So it's 2.02. There's 1 oxygen at 1600, 16.00. So that is 16.00. Okay. So we have a total of 18.02, and that is what we call the molar mass. I got a call from GCC. Let me stop here for a second. Hello? Yes. Okay. All right, so as I was stating here, that number for H2O, 2 hydrogens, this is for hydrogen, this is for oxygen, 2 hydrogens at 1.01 for each hydrogen, it's a total of 2.02, and 1 oxygen, it gives me a total of 18.02 grams per mole. Grams per mole, that is the molar mass for water. Okay. You may also see it as the atomic weight for water, but it's correct to say, I want to say more correct. It's correct to say molar mass because you're talking about all the atoms put together. So once you do that, if I take the 2.02 for the hydrogens and divide it by the total weight, okay, and I take the 16.01 times 100, and the 16 divided by 18.02 times 100, guess what? I end up with 11.2% hydrogen and 88.8% oxygen, okay? And that is true for H2O, no matter where you find it, okay? And that is the composition of water. And in the lab, you know, being an organic chemist, we will make new compounds. This is what we do. We'll get the compound, make it, and then clean it up and then send it up for analysis. We had an idea of what we thought based on other information, but this type of information will confirm it further, and we will determine the percentage of copper, oxygen, hydrogen, sulfur, nitrogen, whatever you needed to look at. And anyway, that's how that's done. So that is the law of definite composition. All right. So I didn't realize my video was off. Okay. So that's the end of chapter 4. Let's take a quick 15-minute break, and then all right. Now, any questions, comments, concerns? Oh, all righty then. Well, let us continue with chapter 5. And in this particular chapter, we're actually going to start getting a more detailed picture as to how the atom is put together. At least what the models have shown. And a lot of it was based on the work, obviously, from J.J. and Rutherford and a number of other scientists that we don't really get into, but there's just multiple different scientists. Now, one thing about this, let me share back to the periodic table. I have my periodic table marked up as follows. If you notice on the far left, I have numbers going from 1, 2, 3, 4, 5, 6, 7. Okay. Now, what that represents are energy levels. Okay, so the first one starts with hydrogen and goes across the periodic table to helium. That's energy level number 1. Number 2 is lithium to neon, sodium to argon, okay, et cetera, et cetera. So there are 7 of these energy levels. Okay. Now, the one way to look at that is that think of them as I stated, 7 energy levels. So one thing, let me draw a picture here to kind of do a side view, if you will. We can't do it with this. So we have the nucleus in the center, okay? Now, we have 1, 2, 3, and I'm only going to go 3 energy levels. So I'm not doing the full circle. So we got the first energy level, second energy level, third energy level, and if we were doing more, we'll go across to all the way to 7. So it is these energy levels of specific distance from the nucleus, okay, where these electrons exist. So the first energy level, second, third, all the way to seventh. Now, within, we're going to learn within these energy levels, there's going to be what are called sublevels, specifically orbitals. These electrons exist based on the model in specific orbits. Okay. Now, with anything, when we start building up electrons, we start at the lowest level and then we continue and move on until we fill up the next level. Okay, so keep that in mind. So this is like a cross-sectional view with 1, 2, and 3 over here. Okay, the periodic table keeps us in mind that we're going to 7 energy levels. So with that information, you can see that the atoms going down the periodic table get bigger. Okay, because those electrons, let me clear this mess up a little bit. Those electrons, for example, lithium, if we look at lithium and compared to, say, potassium, well, the fact that potassium is in the 4th energy level tells you that it is, those electrons, not only do they have energy level 1, 2, 3, and 4, but the biggest energy level they have is layer number 4. Okay. Yes, everybody has it. Start the first one. 1, 2, 3, and 4. We fill up electrons as we build bring in electrons to fill them up. Hydrogen, there's only 1 energy level, the first one, the very first one. But when we move up to potassium, we got 4 energy levels. So that in itself tells you that as you go down the periodic table, guess what? The elements get bigger. As you go down the periodic table, the elements get bigger. Okay. Now, since we're talking about electrons and these energy levels, the outermost energy level is called the valence shell, the valence level. Okay, the valence. That is the outermost shell. So potassium, I can denote potassium here, has 1, 2, 3, and 4 energy levels. I'm not making the full circle. I'm just doing quite. So we got the first one, second one, third one, and the 4th one here. Okay. And so when we start adding electrons to potassium, we build up in the first energy level, and then the second, fill up until we end up at the last energy level. Okay. That is called the valence layer, the valence shell. That is the outermost shell that electrons exist. Okay. Now, down, if you look at the, let me clear this up a little bit, change a different color. If we look at the Roman numerals of your periodic table on top, Roman numeral 1A, this would be 2A. We got 3A, 4A, 5A, 6A, 7A, and 8A. Keeping in mind that magical 8 number, okay? Those are Roman numerals. If you're not familiar with that, I equals 1, double I is 2, triple I is 3. Think about the Super Bowl right now. He uses Roman numerals, 57. Okay. I and V represents 4. That means when that I is in front of V, V is 5. When that I is in front, you subtract 1 from 5 to give you 4. V is 5, and then we go VI, and so the I is after the V, so that is 6. And then VII, that is 7, and then V triple I, that is 8, okay? Now this is true for only those elements that have the A in the same group. So everybody in 1A has, guess what? 1 valence electron. Potassium has 1 electron sitting out here. Okay, it has a total of 19, but of those 19, 1 of them is out here all by itself. Sodium is the same boat, 1 electron, okay? everybody in group 1A has 1 electron in their outermost shell. Now, if we look at group 5A right here, everybody there has 5 electrons in the outermost shell. Okay. What about group 7A? What would you guys think based on what I just told you? Everybody in that group, how many valence electrons would they have in group Roman numeral 7A? What do you think?
7.
Exactly. Okay. Exactly. and more on that. And so everybody in group 8A right here has 8 except helium. Helium has 2. Okay. Everybody else from neon down has 8 electrons in the outermost shell. The outermost shell is going to vary in diameter because you go down the periodic table, you get a bigger one. And this is why these gases, these are all gases, what we call noble gases, are considered inert. They don't react. Why? Because that shell is full with that magical 8 number. That magical 8 where you got 8 electrons around the outermost shell. It's difficult, I shouldn't say impossible, but it takes a lot of energy to remove an electron from that outermost shell that has 8. At the same time, you can't really add electrons because there's no more room. 8 is maximum you can occupy. So it needs to go up to the next energy level, which is from an energy perspective, not very favorable. Okay. And so the point is this, that all of these elements, they're striving to obtain that magical 8. And they do that by either gaining electrons or losing electrons. And when you gain electrons, you gain more negative charge, so you end up with a negative charge. And if you lose electrons, you lose negativity because of the negative charge, you become positive. Put this in long-term memory. All metals want to lose electrons, okay? So all these metals, and remember, use a stair step to tell you who the metals are. They want to lose electrons. And when they do lose electrons, they end up with a net positive charge, okay? All non-metals, it's these guys here, except the noble gases, want to gain electrons. And when they do that, they end up with a net negative charge. This negative and positive losing and gaining electrons creates what are called ions, okay? Or you may know them as the term electrolytes when you're taking a drink and you gotta replenish your electrolytes, because as you perspire, you lose electrolytes like sodium, potassium, and chlorides, and a number of them. So you need to ingest more electrolytes to get those electrolytes in you, which are important because these electrolytes are what conduct electricity and carry current and carry messages, electrical messages in your body, okay? And so when you're eating potassium on your French fries, you are not eating the potassium metal, you're eating the potassium ion. The same is true with calcium and any other. You are eating or drinking the ions, which are the elements that have either lost or gained electrons. And how many they lost and how many they gained depends on where they're at in the periodic table and how close they are to gaining, that magical 8. All right. So more on that in a bit, but we're gonna use this periodic table quite a bit to do a lot of get a lot of information I just talked about. So we don't really have to sit there and memorize all this. I mean, you just look at the element on this periodic table and its position, and one, tell me if it's a metal or non-metal, which then tells me if it gains or loses electrons. And then its position would tell you how many electrons it lost or how many electrons it's gained, okay, to form the ion. It can also tell you by its position in a periodic table how big it is relative to another atom. We can do those type of predictions, okay. So a ton of information can be obtained. All right, so earlier we talked about the electrons being so small that for all intents and purposes, we give it a relative MAU, atomic mass unit, of 0, being massless. Okay, keep in mind that in reality it's not massless, but it is so small that it behaves like light. Okay, these electrons are so tiny that they have properties of light. And so in order to explain them, we got to kind of touch on light a little bit and some of the properties of light. We're going to get into that just a tap. Okay. So the way light propagates through our space is through light waves or waves. Okay. And if we look at this describes a wave of some quantity length. Okay. And now if we take that wavelength, which consists of hills and valleys as it's traveling, okay, if we mark a spot, let me change the color here, somewhere on that wave, let's say from this point on this particular mountain, and then we might mark the same spot on another mountain, that's one new wave of being occurring. That distance there, we call, this is lambda. This is the Greek symbol lambda. We call that the wave length. Now I'm going to use the term electromagnetic radiation. Now, that doesn't mean it's something like just X-rays or something deadly. The radiation, the term radiation amplifies all the wavelengths. There is a scale of wavelengths. On one side, we have radio waves, okay? If you listen to the radio station, that's electromagnetic radiation. On the other side, you have very powerful wavelengths called gamma rays and X-rays. And in between, somewhere in that scale, are the light wavelengths of light that we visualize, that we can see. There's a whole gamut of electromagnetic radiation that we can't see because we don't have the sensors. We have instruments that pick them up, but our eyes can only pick up on a very small amount of electromagnetic radiation. Okay, so that is called the wavelength. Okay, so we have a hill in the valley, also called crest, and throw either one, hill, valley. Now that wavelength is consistent no matter where you pick the point. If I pick the valley, I pick the same valley in the next wavelength, that distance is still the same. Or if it's down the mountain, if I pick that spot, well, I pick the same spot in the next wavelength, that distance is a wavelength, okay? Now, the frequency is denoted by how many wavelengths occur within a given time unit, specifically within 1 second. Think of it as a beat, you sit down, you may get like 10 beats, your heartbeat, figure out how many beats you have in a second. Or, so you can take your heartbeat and count them over a minute and break it down to how many heartbeats per second. Okay, so a frequency is how many wavelengths can go through a specific time of 1 second. We're all familiar, should be, maybe not familiar with the frequency. For example, your computer, your cell phone, it's operated at a certain frequency. You may recall the terms gigahertz. You've got a processor operating at 2 or 3 gigahertz. That's how many, that's pretty fast, pretty fast considering back in the 80s when I got my first computer, we're like in the megahertz, very, very slow. And anyway, so we got the wavelength is the distance between two adjacent waves. And then we have the frequency is how many wavelengths are completed within 1 second, okay? Within 1 second. All right. So here we have 2 wavelengths. And if we look at the top one, okay, we see the wavelength going from say this point to this point. Let me change the color. And that's its particular wavelength. Whereas we look at another one and we got a point from here to here. That distance, that's lambda. You can see here that the distance between the top and the bottom is quite different, right? So we have a long wavelength relative to the bottom, which has a short wavelength. Now, what's associated with long wavelengths is that they have a low energy associated, okay? And a low frequency. Low frequency. Compared to those wavelengths, that electromagnetic radiation that has short wavelengths, they are high energy, okay? And high frequency. Okay, you can see here within, let's for example, if this was a time of 1 second from this point to that point, it looks like the top one can only get like 2 wavelengths, maybe 2 wavelengths within the time span, whereas here you got 1, 2, maybe 3 wavelengths within the frequency. There's more hills going through within that 1 second than there is in the top one. Okay, so the frequency is high for the bottom example, and it's low for the top example. This could be something like X-rays. And this could be something like radio waves. Now, the radio waves are very big. They're in the meter length, okay, with respect to wavelengths. Whereas X-rays are extremely, extremely tiny. We know that radio waves, to our knowledge, are not very destructive. Things block them very readily. Buildings block radio waves, they get affected by the environment. Whereas X-rays do not. X-rays can shoot right through you, okay? They get blocked if you got like real thick building or lead to interact with it, but by and large, those X-rays are very small and they just penetrate right through you, okay? So radio waves have low energy. X-rays, for example, have high energy. Okay. All right. Okay, so in this case here, it says which wave has a higher energy and which has a lower energy. You can see that B, being short in the wavelength, would have the higher energy, and A would have the lower frequency. Okay. Now, this is the spectrum I was talking about. This is the distance from, on the right side, we have radio waves. Same radio waves that you listen to in your car radio, for example, okay? Whereas on the far left, you have gamma rays, extremely high energy, very destructive electromagnetic radiation. Now, this spectrum is not to scale, but what our eyes can see are right in here. That's it, very small relative to the rest of the wavelength. And it's only simply because there's in your eye, there's a specific cells. There's 2 types of cells. There's one called cones, which are sensitive to color, and there are rods that are sensitive to grayscale. And you think about it, next time you're driving in the dark, look around. Everything, unless light hits it, everything's grayscale until headlight hits it, and then the color pops out. So in the nighttime, you're working in the grayscale area. In the daytime or whenever there's light, then the color cones take over. Okay. We got right above the radio waves, we have microwaves. Microwaves are, with respect to energy, are not as energetic as even the visible wavelengths. And so are they hazardous to you when you're microwaving something? Well, the thing is that anybody have any idea or ever thought about next time, every time you use a microwave, how things get hot? How you can stick a pack of popcorn in that microwave and voila, you have your popcorn made. because from an energy perspective, relative to the rest of the electromagnetic radiation, microwaves are not very high in energy. And what's happening with respect to your microwave is the water molecules in the food or whatever you're heating absorbs this energy. Okay, so the water molecules pick up the energy, they excite the molecules. Okay, the water molecules are being excited, and they're not going to hang out there in the excited state very long. They're going to drop back down to the ground state, and in doing so, they're going to give up some of the energy they absorbed. But in the water state, it's going to give it up as heat, and so that heat then is transferred to the rest of the material, and voila, you got your food gets hot. Okay. Infrared is right below visible. UV light is above the visible. Okay, and it can be very destructive. UV light, obviously, that's what's affecting your melatonin in your skin and darkening. You get darkened up if you spend a lot of time out in the sun. But too much exposure can cause all kinds of problems with your skin. Cancer can affect plants out there, the crops, and too much UV radiation could be a problem. Up to recently, the ozone layer up in the atmosphere, which protected us from a lot of UV radiation from the sun, there was a big hole up there. And roughly 40, 50 years ago, they banned a lot of propellants that were causing problems with the ozone. And I guess for the first time in years, they've come out and said that the ozone hole it essentially created a hole up there. If you notice, maybe not, but if you notice that the cream that you use to protect your skin, that number has really increased over the years to high values. And that's because the amount of UV light that is we're being hit with has increased. But they just shown that the hole up there, the ozone hole, has been repaired, which is good news. And hopefully the UV light to us that we get exposed to will decrease. Okay. And then above that, you got the X-rays, very powerful, the strength, and the gamma rays very strong. So be familiar with the scale, radio, microwave, etc. Knowing that the radio waves are the least energy related compared to gamma rays. Okay. All right. Now, the previous chapter we had talked about good old JJ and Rutherford, 1900s. Well, we're back to the 1900s. Here's another scientist, physicist by the name of Max Planck. There's an institute named after him in Europe, but another famous scientist. He proposed a very controversial at that time idea that energy was emitted in small bundles. It wasn't continuous, but it's like little bundles, like little shots of energy. He called them quanta. Okay, quanta. That is, energy is not a continuous emission, but energy was of a specific amount of energy, which is associated within a specific wavelength. Okay, and he defined his unit of energy as a photon, hence the old photon torpedo business, right? All right, so we use the term quantize, that these are energy levels at a specific amount of energy, So those 7 energy levels I spoke to you about on the product table, those are quantized energy levels. They are going from from energy level 1, there's a specific amount of energy associated with that, to number 2, to number 3, etc., etc. I just got a message that my internet connection is a little bit unstable. Hopefully we won't get disconnected. One way to look at it is this diagram here, where in the far left you see this wedge and the ball's rolling down the wedge. That would represent a continuous amount of energy, all one shot. as compared to the image on the right, which is represented by stair steps. The stair step represents a specific quantity of energy from the ground to the next step. Okay, so you can see going from the ground to say this level, a very specific amount of energy, and the same from here to here. Okay, etc. All right. Now, we have Max Planck with his idea of quantized light. Here comes another scientist, Niels Bohr. Okay, we propose that electrons, being so small, and exhibit lights, properties of light, but he also proposed that these exist in orbits of distinct energy levels. Okay, so he would kind of borrow from Peter to bring into Paul here. Okay, so he borrowed Max Planck's idea. Okay, and proposed that these electrons are very specific energy levels. So we ended up with the Bohr model with respect to electrons in 1913. Max Planck was in the 1900s, right? We had J.J. Rutherford, Einstein's involved in here. We had Pauli, the list of scientists. There's something about this time period that really amazes me. It's like all these scientists just boom got together, and all of a sudden all these models and theories start popping out. You know, in the 1900s. We haven't seen anything like that over the years. You know, yes, we get advances, but it's like, you know, a little bit here, a little bit there, but nothing like this time period. Okay, so we got Bohr's model 1913 that the electrons are quantized. Okay, they orbit in specific energy levels. Okay, and there are 7 energy levels of which are related to the periodic table, as I showed you, and those levels are called periods. Those Roman numerals that I talked about earlier on the periodic table, we call those groups. Okay, so we have the groups going down and going down, but going across the 7 energy levels, those are periods. Now, one interesting aspect about the groups, if you look at the periodic table behind me, you look at group 1A under hydrogen, they all have in common one valence electron in their outermost shell. And all of them react very similar. That's why they're placed in that group. And they all react very similar because they all have one valence electron. Remember that all chemical reactions occur, it's just a function of electrons either being transferred from point A to point B or being shared. Okay, we're going to learn that to make bonds, we're either going to transfer electrons from one element to the other, okay, to end up with positive and negative charges that get attracted to each other, or these electrons are going to be shared amongst the atoms and form a bond. Okay. It's all about electrons, but specifically, it's all about the electrons on the outermost shell. That's where all the actions happen. Okay, so each orbit, each has a specific radius and a specific energy. You know. All right, so it's denoted as follows, where we have the nucleus, and then these dotted circles represent the orbits where electrons exist, energy level 1, 2, 3, etc. Now the question was, well, how do we come up with this? How do we know that this is what our model is? Well, what came about is what is called light spectrum. And let's explain how this happened. So what he did, again, Bohr, he looked at behavior of gases that were sealed in a tube. We know them as neon lights, okay, or, you know, and it's a gas in the tube that electricity is passing through them, generating a light. Okay, just like the fluorescent light bulbs that you may have at home or, you know, up in the lab. Okay, they are gases that electricity passes through them. the molecules get excited, okay? Then once they get excited, they go back to the ground state and they have to release that energy that they picked up moving from point A to point B, and they release it as light. So that's how the light works. Just like the light works on your screen right now, as you're looking at your monitor, you're seeing all these lights coming out. It's these molecules that are picking up that energy from some place to get excited here in front of your screen so you can visualize what's going on. Okay. All right. So what he did, he was able to study these discharge tubes, okay, fluorescent light bulbs, basically, but they were filled with different gases and different materials, okay? And what he did is he took that light that was emitted from these tubes and he ran them through a prism. Now, a prism, what that does is takes the light and breaks it up into the different wavelengths, okay? Much like a rainbow. You know, after a rain, you see the clouds, you look up, you see a rainbow. Well, the reason you see a rainbow is because the light droplets up there are taking the light and they're breaking it up into the different wavelengths, specifically the wavelengths that we can see, okay? The UV light, and hence we see the rainbow, okay? And that rainbow that we see is called an emission light spectrum. And it differs differently from each gas. Okay, so here's the layout. So we have the bulb over here, okay, electricity, and obviously like a fluorescent bulb emits light. So we run it through some slits, and all that does is just focuses the light, okay? Here's the prism, and the prism then takes the light and it breaks it up into specific wavelengths. So you would think, okay, we'll just get maybe one color here and maybe nothing, but what's happened, the light is broken up into different visible light wavelengths, and you end up with a bar here. Here's one right here, the violet, the blue-violet, the blue-green, and the red, okay? Each with a specific wavelength, a value. This is nanometers, okay? And this could be done, the instrument will give you this readout. This particular line spectrum is specific for hydrogen. It is the fingerprint for hydrogen gas, okay? And that's one way to identify what type of gas you're working with by running it through this process and analyzing the light spectrum. And that's how one way we can look at light from space, and a lot more complicated than I'm just stating here, but able to break it up and determine what type of gases or elements are up there without, you know, going up there to get a sample, because we're doing analysis of the light, okay? So, in doing this to a variety of different elements listed here, you got N metals, and not just gases, but we got lithium, sodium, potassium, and each one has their own specific emission line, okay? Its own specific colors, and that's the fingerprint for that particular element. But what we are observing here to give us a spectrum are these electrons that are being excited from the ground state. When I say the ground state, that means the state where that electron, the energy level that electron is normally is at, whatever level it may be. And when it absorbs energy from an outside source, it kicks it up to the next energy level. Okay, when that occurs, as I stated about Mother Nature, it's not going to be in that excited state very long. What goes up must come down, so to speak. So when it drops back down to the ground state, the law of conservation of mass and energy states that whatever energy gained, it's going to be the same amount of energy lost. And what happens here, that the energy that is lost is given up as light, and we see it in this light spectrum. And we can look at those lines and we can do an analysis of them, break them up, and actually determine that these electrons are in specific energy levels. Otherwise, we wouldn't see this light spectrum. Okay. And this demonstrates what I just talked about, where in the ground state, okay, whatever state that may be, in the stable state, this red dot represents an electron orbiting around some atom, and it picks up energy, okay, and it doesn't have to be electricity, it can also be light, it could be heat, but it picks up energy of whatever source and kicks it up to the next energy level, okay? And then it's going to return back to the ground state, but in doing that, it will release that energy it picked up as light, and it does it, you know, maybe even heat. And it's all around us, okay? If you have an electric stove and you turn on the heat in an electric stove, what happens to the element? It turns red because the electricity running through that metal, there's a high resistance in that metal. It is exciting the molecules of that metal, and then it's going to give off the heat, the energy it has picked up. It's going to give it up as heat, and your metal, you know, lights up. The element lights up, and you're able to do some cooking. You know, the lights that we utilize around us, same principle all around us. All right, so it's a matter of energy, specific energy. Okay, so what we have based on this information and analyzing the light spectrum is that we have 7 energy levels of 7 periods. But we also learned that based on our model, that we have what are called sublevels, which are denoted by the letters S, P, D, and F. These sublevels, another term used for them are orbits or orbitals, okay? And the first energy level only has one sublevel, we call it the S, okay? And we denote that its notation is the 1 in front of the S. So that denotes the first energy level in the S orbit. Okay, keeping that 1 in mind, looking at the periodic table behind me, is the hydrogen on one side and the helium on the other side. Those electrons occupy the first energy level, the S orbit, okay? The second energy level, which again, looking at the periodic table behind me, you have on the far left, the first 2 columns, Roman numeral 1 and A, which are the S orbits. And then when you shoot across, you end up across into boron. Looking at my periodic table, you see boron, and that starts off a second sublevel called the P's, okay? So in the second energy level, there's only 2 sublevels, 2 orbits, the S and the P, okay? Now we look at the third energy level, which starts off with sodium, check your periodic table, and we go across, we continue with the S orbit, it has an S orbit. There's also P orbits in the third energy level, but we introduce a third energy level called the D orbits, okay? The D orbits. I haven't talked about the electrons and where they exist and so forth, but here's the thing that can be confusing at times, and I want to see if I can get it straight here. Now, even though in the third energy level, the D orbits begin, they actually come, these D electrons come from elements in the 4th period, okay? And here's the thing, okay? These orbits, S, P, and D, come from mathematical equations beyond the scope of Chem 130. And there are some crazy looking equations, trust me. And anyway, they are mathematical equations. The whole model, the whole idea of all this is basically all pure. To start off with the line spectrum. But with that information, a model has to be built. And of course, with any model, there's always mathematical equations. And so hence the result are these orbits that were generated through the model. Okay. And the four types of orbits are called the S, P, and the D, but there's more on those in a bit. But the D orbits, though they start off in the third energy level, okay, in the third period, they actually come from elements that are in the fourth period, okay? And that's because the mathematics that created or had the D orbits put it such that their energy level wasn't really in the predicted fourth energy level, but actually one level in, okay? So keep that in mind, that even though the Ds begin in the third energy level, that those electrons actually come from elements in the fourth period. And then there's one more, and those are the F. Let me clear my mess up here. The F orbits begin in the fourth energy level, okay? And so we have four types of orbitals where these electrons exist: the S, the P, the D, and the F. And I'm assuming as the elements, we find more and more elements and bigger, we're probably going to get into the G, but we're at the F right now. Now, the other aspect, as I just explained, that the Ds, this specifically, the Ds come from the fourth period elements, okay? And the 4D would come from the fifth period elements, okay? The same, similar with the F. When the F show up in the fourth period, they actually come from the sixth period elements. Okay. And so if we had a 5F, then that would come from the seventh period elements. Again, because those orbits they didn't anticipate, well, it turns out that the energy level for the F orbits are not at the energy level that the elements come in, but actually are 2 energy levels less in the energy level. So it's 2 away from where they're at, 1 away for the Ds, okay? I'll give some examples here in a bit, maybe to straighten up a little bit of any confusion. And so we have the S orbits, the P orbits, the D orbits, and the F. Note something here, that everybody from 1 through 7, we can go all the way to 6 and 7, all of them, everybody has an S orbit, okay? It's just different size. We got the 1S, maybe this size, and then the 2S, the 3S, the 4S, and now we got the 7S, which is like a beach ball. Go from a golf ball to a beach ball. Exaggerating, but that's what's going on. The Ps don't come into play until the second energy level, but after that, they are in all of the other energy levels, okay? So you go from 2P all the way to 7P. The third energy, the same is true. So we got 5D, 6D, and 7D. They don't come into play until the third energy level. So from that point forward, you got 3, 4, 5, and the same with the 5F. Right now, we stop at the 5F because there's only 7 periods right now with elements. And I went too far. Yeah, this will be fine. 7D. No, we don't have an 8, so there won't be. We don't want to stop at the 6. Okay. All right. So that's how that works. Now we're going to talk about each particular orbit. All right, and this here is the kind of a diagram, kind of represent 2-dimensionally what we're talking about. But the first energy level between hydrogen Yep, hold on. The first energy level is between hydrogen through helium. Okay. The second energy level starts with lithium, goes across all the way to neon. The 1, 2, 1, 2, and 3. The 3 starts from sodium all the way across to argon. And then the 4th starts from potassium all the way across to krypton. Okay, but then we start entering the other elements. I'll give you some more information on those in a bit. Okay. Now, there also, which is pretty cool because we can use the periodic table to describe the electrons and what orbital those electrons are in. Okay, based on their position on the periodic table. All right, so let's regroup for a little bit, and let's talk about the orbits, the orbitals themselves. Now, again, as I stated, these orbits are nothing more than mathematical equations, and mathematical equations in 3 dimensions. And if you take those mathematical equations and plot data on them, you generate a plot, specifically a 3-dimensional plot. And when that occurs, you have this plot that represents where in space there's a high probability of finding an electron for that particular orbit. Okay, so in the s orbitals, okay, I'll finish this slide and we'll stop it here. The s orbitals can have a maximum of 2 electrons. This again comes from the mathematics of these orbits. Okay, point number 1. Let me get my pen. For the s orbits, there's only one s orbit, okay? And each orbit, one s orbit can handle a maximum of 2 electrons, okay? And we denote that by saying s superscript 2. That tells us that s orbit, so this is like 1s superscript 2, that tells us the first energy level, s orbit, superscript 2, 2 electrons. You know, if it was 1 electron in that orbit, it'd be 1s1. That would be hydrogen, 1s superscript 1. 1s superscript 2 would be helium, okay? Now, the p's, there are 3 p orbits, 3 of them, okay? And each one can handle 2 electrons, and since there's 3 orbits, remember, every orbit can only handle maximum of 2 electrons. And since there's 3 orbits, there's a total of 6. So we denote that maximum. We go from P1 all the way to P6, okay? And then the coefficient can be from 2 forward. I'm going to leave the coefficient out. The d orbit, there's 5 of them. There's 5 d orbits. Each orbit can handle 2 electrons. So there's a maximum of 10 electrons, maximum for the d. So we denote that from d1 to show that there's 1 electron in that d orbit, and it goes all the way to d10. Okay? Again, with the coefficient in front, depending on what energy level it's at. And then finally, the f orbit has 7 electrons, 7. Okay, that tells you that there's a maximum of 14 electrons for the f orbits. There's a difference here. 14 electrons for the s orbit, not the maximum electrons for whatever energy level it's in. We'll show how that differs. So we can write that with the f superscript 1 all the way across to superscript 14. Again, let me rewrite this. It will go from S1. Let's keep it consistent here. We'll throw in the numbers here in a bit. So the S can be written from S1 all the way to S2. There's 2 electrons. The P's from P1 to P6, D to D1 to D10, F to F1, superscript F to F14. So the superscript denotes how many electrons there are in that specific orbital. And then there's the coefficient, which can vary from 1 through 7, depending on which orbit we're talking about. And we use this notation to describe the element and to describe how the electrons for the element are placed in these different orbitals, okay? And as we learn to do this, we're going to learn why certain metals want to lose electrons and other metals want to gain electrons, okay? Because it's related to these orbits and the electrons that they have, and how many they can lose and how many they can gain. All right, so let me stop it here. Okay, and we will continue. So slide 19. Have to share. All right. Okay, well, thank you for your attention. We'll see you all on Friday. Don't forget that first exam. Okay. Check the time, verify the time that you have, and then adjust accordingly. Give yourself plenty of time, and it's going to be straightforward. Nothing, hopefully, to confuse you. I'm not trying to confuse you. All right. Any questions? Comments, concerns?
I
No?
have one question.
Sure.
So I went to that lab today with the other teacher,
Yes.
and it went good. But I have lab 2 from last week. Do
Uh-huh.
you want me to email you a picture of it completed, or do you
Oh,
want me
no,
to
just bring it in. You'll be all right.
Okay.
Okay.
Okay. Thank you for letting me do that, by the way.
Yeah, no worries.
Okay.
Okay.
I'll bring them both.
Okay. Any other questions? What we did here for future reference, if you have a time conflict for our labs on Friday, we do have we are the last of the week for that particular experiment. And so, but there are like 4 labs in the earlier that week. So if you need to make up a lab, we can send you to one of those days. Okay, just keep that as FYI. All right, if there are not any questions, I will